According to another hypothesis, Sirius B exhausted its stellar fuel around 120 million years ago and became a red giant. Shortly after, it shed its outer layers and transformed into a dense, extremely hot white dwarf. This explosion destroyed the protoplanetary gas and dust disk surrounding the young star system at the time, preventing planet formation. Currently, Sirius A and Sirius B orbit a common center of mass at moderate distances, completing an orbit every 50 years. Over the next 60,000 years, Sirius will gradually approach Earth, reaching a minimum distance of about 7.5 light-years, then slowly move away. About 66 million years from now, Sirius A will undergo a similar fate, a brief but intense brightening thousands of times its current luminosity, followed by complete fading from the sky. After moving away from the ultraviolet radiation and stellar winds of Sirius, we reach Wolf 1061, a red dwarf located 14 light-years from Earth. Wolf 1061 has about a quarter of the Sun's mass and 30% of its radius, with a surface temperature of 3,272 Kelvin and luminosity only 14% of the Sun. 3 rocky exoplanets orbit close to this star: Wolf 1061b, Wolf 1061c, and Wolf 1061d. Wolf 1061b is very close to the star and likely tidally locked. Its day side is extremely hot, making an atmosphere nearly impossible. Wolf 1061c lies in the star's habitable zone and could potentially harbor liquid water. It is about 3 to 4 times more massive than Earth and classed as a super-Earth. Wolf 1061d has a distant orbit outside the habitable zone and is likely unsuitable for life, though it is scientifically interesting for studying planetary evolution. Wolf 1061 is located at the edge of the local interstellar cloud, a hot but sparse hydrogen region that poses no threat to Earth. Further away, we encounter AP Colomb, a red dwarf 27.4 light-years from Earth. This young, unstable star has unusually high lithium content and a tendency to flare, making it an important case study for early stellar evolution. It appears too young for full planet formation. At 37 light-years from Earth lies Glysa 370, an orange dwarf with a single known exoplanet, GLSA 370b. This rocky super-Earth resides in the habitable zone and may have liquid water and a moderate climate, making it a promising candidate for potential life. The Castor system, 50 light-years away, is a complex 6-star system, including Sirius-like binaries and red dwarf pairs. While no confirmed exoplanets exist yet, rocky planets may be present. All of these stars are part of a structure called the local bubble, spanning about 300 light-years. Formed by successive supernova explosions, it is a hot, low-density gas cloud. Despite the energetic particles, Earth is protected by the solar wind and its atmosphere. Finally, extreme endpoints of stellar evolution include black holes and hypothetical quantum black holes. Black holes can affect nearby stars and planets, but do not indiscriminately consume everything. Stellar mass and supermassive black holes grow by accreting gas and stars, potentially forming new planetary systems while destroying old ones. Each object in the universe is unique, and studying stars and planetary systems not only helps us understand the cosmos, but also humanity's place and evolution within it. NASA confirms that Voyager 1 was the first human-made object to escape the Sun's influence and cross into the cold, dark expanse of interstellar space. But this isn't just another spacecraft. It is more like a ghost, whispering faint signals from the silence of the cosmos. Launched in 1977 for what was expected to be a 5-year mission, Voyager 1 now drifts nearly 14 billion miles from Earth, still active after almost half a century. It has gone farther than any other creation of humankind, venturing into a region no machine had ever reached before. Despite carrying less computing power than a digital wristwatch and storage smaller than a single image on your phone, it continues to transmit messages from beyond the solar system. Instead of answers, Voyager often leaves us with deeper mysteries. And recently, it has surprised scientists yet again by revealing something no one anticipated. The mission itself was born out of a rare cosmic opportunity. In the early 1970s, astronomers discovered that once every 176 years, the outer planets, Jupiter, Saturn, Uranus, and Neptune, align in a way that allows a spacecraft to slingshot from one to the next, gaining speed without using much fuel. Engineer Gary Flandreau at NASA's Jet Propulsion Laboratory noticed this planetary highway with nothing more than paper, pencil, and calculations. Instead of taking decades of propulsion, a probe could reach Neptune in only 12 years. The timing was critical. The alignment would peak in the late 1970s, and missing it meant waiting another lifetime. NASA acted quickly, launching 2 spacecraft just weeks apart in 1977, Voyager 1 and Voyager 2. At first, their goal was modest: study Jupiter and Saturn up close, then shut down. But the spacecraft proved far tougher than expected. They endured radiation belts, freezing darkness, and countless hazards. Alongside scientific instruments, each carried a golden record: images of life on Earth, greetings in dozens of languages, music from around the world, and sounds of nature, a time capsule cast into the ocean of stars. The discoveries began almost immediately. When Voyager 1 reached Jupiter in 1979, it sent back astonishing images. The gas giant was not a still, lifeless world, but a planet alive with storms and violent activity. Its moon Io stunned scientists with erupting volcanoes, the first ever seen beyond Earth. A year later, Voyager 1 captured Saturn's dazzling rings and turned its cameras toward Titan, a world hidden beneath a thick orange haze with signs of a complex atmosphere, perhaps even ingredients for life. Voyager 2 later continued to Uranus and Neptune, becoming the only spacecraft to fly by those distant worlds. Meanwhile, Voyager 1 pressed outward into the dark, leaving its cameras behind to conserve power, but keeping its instruments running. What made these encounters even more remarkable was the technology. With only 69 kilobytes of memory and tape recorders for data, Voyager's brain was far weaker than today's simplest devices. Yet it navigated asteroid fields, magnetic storms, and frozen moons flawlessly. Each planet it passed transformed our view of the solar system. But its greatest revelation came much later. Decades beyond Neptune, Voyager 1 approached the mysterious boundary where the sun's influence ends, the heliopause. Scientists long debated where exactly this invisible frontier lay, where the solar wind gives way to the interstellar medium. On August 25, 2012, Voyager 1 crossed that line. Its instruments detected fewer solar particles and more high-energy cosmic rays from ancient supernovae. Humanity had officially entered interstellar space. Yet something was strange. The direction of the magnetic field did not shift as expected, raising new questions. Had Voyager entered a transition zone, a turbulent sea where solar and galactic forces mix? The boundary, it seemed, was far more complex than a simple line. Even more mysterious, the probe soon detected bizarre plasma fluctuations. Instead of a calm, uniform environment, the interstellar medium was textured with sudden rises and drops in density, as though Voyager were drifting through clouds left behind by exploded stars. These may be remnants of long-dead supernovae, cosmic fossils millions of years old. Voyager was not just traveling through space, but also through history, brushing against the ghostly fingerprints of ancient stars. Despite the harshness, Voyager still carries a message from us. Fastened to its side is the golden record, designed to last billions of years. Greetings in 55 languages, sounds of nature, laughter, music, and even the beating heart of a young woman. Carl Sagan, who led the project, called it a gesture of hope, a way to say this is who we are to any civilization that might one day encounter it. Now more than 22 billion kilometers from Earth, its weak signals take over 20 hours to reach us. One by one, instruments are being shut down to conserve its dwindling power. Sometime in the next few years, Voyager 1 will fall silent. Yet even without energy, it will continue drifting through the galaxy for billions of years, perhaps passing unknown stars, perhaps never to be found. But its mission has already succeeded. It extended human imagination far beyond the horizon. Voyager 1 began as a scientific project, but became something deeper. A reminder that curiosity and persistence can outlast generations. It carries no flag, no claim of conquest, only questions and a voice that whispers across the dark. We were here and we dared to explore. Even when it stops transmitting, its journey will never truly end. For as long as it sails among the stars, Voyager will remain a mirror of ourselves, fragile, determined, and endlessly curious. And so the question lingers, if this tiny spacecraft built with 1970s technology can travel so far into the unknown, what else might we one day achieve?